Hi, this is my attempt to respond to some of the questions that you raised in the discussion online for the first week of 930K. And I'm answering some of the questions on all of them. Some of them we can talk about in person next week, but I did want to clarify some things, so bear with me. There are two or maybe three big principles that we need to think about for this week as the basic concepts are concepts that you've covered before, and most of you talked about this. And we need to think about them as laying the foundation for a larger understanding. And these are a few of those. One is that randomness is all around us. That's very clear from Londinov's book, and it is something we need to guard against, and we guard against it in multiple ways. One of them is, of course, by deciding on how different two things need to be in order for us to say that they are what we call statistically significant. So we have in the social sciences decided on 1 out of 20. So p equals or is smaller than 0.05, so it's smaller than 1 out of 20. If the probability that something would happen just randomly is less than 1 in 20, we say it's statistically significant. That, of course, is completely arbitrary. It's rare enough, but we really want very often things that are considerably more different. And that is also very susceptible to sample size. So the bigger our sample, the smaller the variation around the mean, the more we're sure that this sample represents a population and not just chance, and therefore it is more likely to be significant. That can become problematic because in large data sets with a lot of data points, just because there are lots of them, even small changes or small differences can become statistically significant just because the confidence intervals around the mean becomes very, very tight. Again, a product of how many observations you have. As a result, we always accompany a discussion of statistical significance, that is, how likely it is to happen just by chance. If it's likely, we didn't get anything. If it's not likely, we may have something. And the we may have something goes to the next step, which is how big is it? So how big is the effect size? Does it matter? And effect sizes come in two major shapes. Although there are variations on these shapes, there's an effect size that tries to look at how much of the variance is explained. The second point is trying to measure what is the difference in standard deviations units, and that's Cohen's d. So those are two ways to do it, and we'll talk more about them when we talk about regression, which is when we talk about percent of variance explained. That's 2 weeks from now, and we talk about an effect size D, and that's 3 weeks from now when we do an ANOVA. We do a comparison of two means divided by the standard deviation. So that's the first thing. The second thing is to remember that the universe is normally distributed. That is, most phenomena in the universe, when they're measured and you take a sample out of a population, will end up with normal distributions. That is just the nature of nature, so to speak, and not everything obeys that distribution, but most things do, and definitely samples out of a population will definitely obey that distribution. So when the universe is normally distributed, most things should appear normal. If they don't appear normal, it's either because we have a problem measuring them well, or potentially the other problem is that our samples are too small. And if samples are small, then they might not reach normalcy. And they might not be normally distributed as an artifact, again, of measurement or an artifact of how small or unique your sample. And remember, even something that happens only 1 out of a million cases still happens 1 out of a million cases. So if something happens in the United States 1 out of a million for 1 out of a million people every day, then every day in the United States, about 350 cases of that would be expected. For an individual, that would be really odd. For the whole United States, that would be business as usual. So this is where it gets hard. And there was the question about, does variance not matter? Well, in some ways it doesn't, in some ways it does. It obviously does, because everything we do in quantitative analysis is trying to explain variance. That is all that we can do. We play with variance one way or another. Without variance, we've got nothing. With variance, we've got everything. So variance is crucial. But the measure of variance itself is highly dependent on your unit of measurement. So imagine this. If we're measuring time, and you've got 1 hour, that is my variance, that's squared, right? So I've got the standard deviation of 1, I square it, I still have 1, that's my variance. If I convert the same exact measure into 60 minutes, now I square it to get the variance, right? If the standard deviation is still 1 hour, I square it to get the variance. The variance in minutes is 3,600. So the measure of variance as we collect it is actually highly dependent on your unit. And that's why we don't pay too much attention to it. What we try to do is try to explain as much of the variance, again, explained in percent of variance explained, not the number. And the other thing that we try to do, and that is important to remember, is we can compare variances if the units are the same. So we can say this sample has a lot more variance than this sample. That works. So you can do something with variance, but not on its own. It doesn't stand on its own because it's so dependent on the unit you have. There was a question about causality. We established causality very simply on comparing two samples. So we take a population and we randomly sample two random and large enough samples. Again, the important thing is random. And how do you get random? That was a question as well. You either use a random number generator, you can find those online, or you draw names out of a hat, or you use random numbers that are in books. It is important to know that computers in general have a hard time producing completely random numbers because computers in their essence are sequential. So they can't produce something that is completely random, so there are ways to manage that. And you can't do it manually. You have to do it in a method that actually does not allow you to have any control over the result. So again, random number generator, drawing names out of a hat. I've done that a few times when I work with teachers, and we randomize the teachers because I want them to see the process and not think about going back to Mlodinov. We always think there's a reason, and that's a way to prevent anybody from thinking that there was any plan or reason behind it. So that's a way to think about it, and the law of large numbers works here. The law of large numbers says if a number is large enough, we're safe. So if you're randomizing two groups out of a population and group 1 gets treatment, group B doesn't get treatment, if they're large enough, they are equal on most characteristics just because we randomize them. And therefore, if we did something to group A and not to group B, and group A has a different outcome, then we know the cause was the intervention, the thing we put at play. Classically, we talk about drugs in drug trials, or curricula in education, or an intervention where we do something specific with a person. All of these work. That's how we determine causality. We call it RCT, or the randomized controlled trial. And for that, again, we need one population and we randomize the participants. That's called the golden standard. That's really hard to do in education because we have intact classrooms, schools, and all of that. We don't tend to break them up. And so we have to find other solutions, and we do things like quasi-experimental, where we compare two classrooms or two schools and things like that. The problem that we have there is then we're not sure if there was something about classroom A versus classroom B that was distinguishing them beyond just the method. For example, they have different teachers, different motivation, different time of day. You can go on and on and on. And that's why we do randomized controlled trial and make everything that happens to the two groups exactly the same, except that one thing they intervene. And again, we draw random samples that are big enough. Big enough usually means 30 to 32 is the minimal size for each group, and then we can have some conclusions about them. If we're worried about specific subgroups, then the question becomes much larger, because then you need to sample for each subgroup at that number. So you quickly, if you want to consider all of these other factors, you need to quickly get to a much larger sample size. When you talk about doing research in your own class, doing classical statistical analysis is usually not very useful, although there are some ways in pre-post designs. You measure what your classroom can do before and after, but having a comparison group and things like that is very, very hard. You can, however, if you're working, for example, in a 6th grade and you're working with a few classrooms that you're teaching the same curriculum, you can start changing things or get together with colleagues and alternate curricular innovations, things like that. You can actually go beyond your classrooms. There is also single subject design, which we're not covering in this class, but it's a really interesting choice if you are doing research in your classroom and measuring specific students. It's very akin to what we do in response to intervention and doing progress monitoring with individual students. If you're interested, I'll be happy to go further. So these are a few comments about what you can do. A few more things that I want to talk about. One is, don't forget to blog today or tomorrow or Friday, or today is Friday, Saturday or Sunday, just as a sense to close off the week and see how are things playing out for you, how are you feeling about the different aspects of the research. A few more small things that I wanted to point out. What do you do with outliers? There's no one answer to outliers. The first thing we do with outliers is identify them. We do that on a histogram. The second thing is we ask, is this even a probable value? So sometimes we have values that are not possible. It's usually entry problem or somebody going outside the regular parameters. So if you see an age and it says 160, that's probably a mistake. Maybe it's 16 and somebody just pressed 0 or something else. So you want to see if it's highly improbable. You go back and you check if there's a paper format. You definitely go back and see if there was a problem in moving it into computer format, which is how we mostly work. If there's something else going on, you want to investigate and see. If there's a reasonable expectation that this was a mistake, you remove the outlier for sure. If there isn't, you have to carefully consider, and one of the things we do later, even if we include it in analysis, is actually conduct the analysis twice, once with, once without, and there are lots of mechanisms to achieve that, but the idea is that we want to see how much does this 1 or 2 or 3 outliers change the overall result. If they change it a lot, we've got a problem. If they don't, then we can include them or not. It really doesn't matter. So you've got to ask yourself these questions. What do they mean? There's actually examples in our data, so that's a discussion we can have next week when we meet. So that's it for this week. There were more questions and we'll discuss some of them on Monday, and I'll see you around.